there, everyone. Welcome back. Happy Easter to all of you. Hope you're all having a really nice holiday. And my Easter has just been kind of been low key. And by that, I mean I ate as much junk food as possible. And I'm just sitting here with all of these empty candy wrappers around me. I'm filled with shame and regret and self hatred. But it's enough self pity. Let's get to work. This is an optimization problem. It's a lot different than the ones we saw in previous examples. The thing is, we have actually a function to look at. My name is covering the question. Sorry about that. We're looking at a linear function, and we're being asked to minimize the distance between any point on this line that I drew right here and the origin, which is just 0, 0. So let's just kind of get an understanding of what exactly we're trying to do here. So we're going to pick just an arbitrary point on the line. Maybe right here is good. And then I'm going to draw a line from that point to the origin. So that would be one example of the kind of line that we're looking for. And I'm going to give us another example. I'm going to pick another arbitrary point, and then I'm going to draw a line from the point to the origin, just like that. So truth is, we could pick any single point on this line. But the thing is, we're trying to find the minimum distance to the origin. We're trying to find a point that gives us the least possible distance between the point and the origin, the point in 0, 0. So we can tell pretty clearly that the blue line is a lot closer to the origin than the green line. So we can sit here all day. We can make some nice little pictures and then decide which of these would be the closest. But it's an awful lot of guesswork, an awful lot of frustrating drawing, and we wouldn't get the exact answer. So we're going to find a different method. We're going to find a better way of finding this point that we're looking for. We're going to use calculus to find the precise answer. And I erased part of that question. Don't know why that happened, but it did. So let's see if we can get a sense of how to use calculus to solve this problem. It may not be clear right away what we have to do, but this is an optimization problem. If you've looked at my previous videos on optimization, remember that we have a few quantities we're concerned with. We always have a quantity that we're trying to optimize. In this case, it would be the distance between any arbitrary point and the origin. That would be the thing we're trying to optimize. And then we also have something called the constraint. It's also going to be just something that we can't change whatsoever. It's a fixed value that stays. So in previous examples, when we're trying to, for example, construct a box, the constraint would be the amount of material available to build the box. We can't magically have more material. So that would be the thing that cannot change. In this one, it may not be clear what the constraint should be. So the constraint's actually going to be related to this linear expression that they give us, this linear equation, y equals 4x plus 7. That's going to be our constraint. Now let's see if we can find the quantity that we're trying to optimize. So remember from before, I drew all these lines, and this distance is what we're trying to optimize. So let's see if we can come up with just a general expression for the distance between any generic point. We don't even know what the point is. The answer is going to be a point with an x coordinate and a y coordinate. They're going to be numbers. We'll find out exactly what those numbers are. But for now, we have no idea. So I'm going to be generic. I'm going to call this x, y. Really imaginative, I know. So this is our arbitrary point, and we're trying to find the distance between that point and the origin. But we can't find the true distance yet because we don't know x and we don't know y, but we're going to find those. So let's see if we can come up with an expression that gives us the length of this line for any given value of x and y, any given values. So we're going to need the Pythagorean theorem. And the thing that kind of tips me off about that is that we're going to have a vertical distance between our point and the origin. We're also going to have a horizontal distance. We have a clear delta x and delta y and delta x situation. That's kind of a dead giveaway that we need the Pythagorean theorem to help us with this one. So I'm going to call this L, L for length, and I want to come up with an expression for L. So L is going to be the result we get when we apply the Pythagorean theorem to this problem. So we have, I'm going to call this, delta x, and then I'm going to call the height of this triangle that I made delta y. So the length is going to be delta x squared plus delta y squared. And actually, it's not just the length, it's the length squared that produces this result. So ordinarily, we would have x squared, a squared plus b squared equals c squared. we have the same thing. I just added different variable names to make it apply more to this particular problem. But it is the same process, the same general idea as doing a squared plus b squared equals c squared. So let's see if we can be a little more specific with this information. So delta x, we can say that delta x is equal to some expression. We can say, in this case, we can see that delta x is going to be equal to 0 minus x, because our origin has coordinates 0, 0. So this is going to be 0 minus x. And I put the little slash through the 0 just to make it clear that that is, you know what, I think it might be kind of clear enough. So I'm going to just make delta x into 0 minus x. And then we have something similar for delta y. Delta y is going to be, you guessed it, 0 minus y. You might be thinking, why is it not y minus 0? Because y is on top and 0 is on the bottom. Because the truth is, it doesn't matter what order they're in. 0 minus x is negative x. 0 minus y is negative y. We know for sure we're going to have to square delta y. We know for sure we're going to have to square that. So actually, it doesn't matter if it's a negative y or a positive y. When we square it, we're automatically going to make it positive y squared. So it doesn't matter if you do 0 minus y or y minus 0. And then the same thing goes for x. But there's one more thing I have to do. I have to make one more modification to delta y. I can't talk today, to delta y, so that we can actually start using our optimization process to find the result that we're looking for. So what I want to do is, instead of a y, I'm going to replace this with 4x plus 7, because we know that's what y is equal to. We have delta y is equal to, and then just like for the reason I said before, it doesn't matter if we have 0 minus y or y minus 0. So theoretically, if this were just y minus 0, it's the same answer we would get if it were 0 minus y. So y minus 0 is just y. So instead of having delta y equals y, I'm going to have delta y be equal to this thing that is also equal to y. I'm going to have delta y be equal to 4x plus 7. So now we have all the relevant information we need to plug in to start solving for this. So I'm going to just take the square root of both sides of this equation, because we know we're not going to want L squared. We're going to just want L for this particular situation. So we're going to have L is equal to delta x squared. So just like with the y, 0 minus x, that just turns into a negative x. And when we square a negative x, we get positive x squared. So that means delta x squared is going to be positive x squared. And then delta y, on the other hand, it's a different story. It's going to be just not just a single variable, but an expression. We're going to have 4x plus 7 squared, because that's delta y. And to get rid of the second power in our L identifier, I just took the square root of both sides. So we don't have an exponent there anymore on the left. What we do have instead is a radical covering everything on the right side of the equation. And I've learned that it's nearly impossible for me to make a satisfactory radical looking thing. So I'm just going to resign myself to using the tools like a cheater. So now we have this thing we need in terms of just one variable. Remember in the pack, why can't I talk today? Remember in the previous optimization problems, we always have to put things in terms of just one single variable. So it doesn't work to have things in terms of an x and a y. We can only have things in one of those variables. And y is already in terms of x. We just put everything in terms of x. So instead of having L as a function of x and y, we now have L as a function of only x, which is really nice and really super convenient actually for our purposes. So let's simplify this a little bit. I'm going to simplify this 4x plus 7 squared. If you want, you could FOIL it, but for the purpose of time, I'm going to go ahead and just do the binomial theorem. So I'm going to leave the x squared alone. That part's not going to change. I'm going to draw the radical first, because it might be easier. You know what? That is pitiful. That is shameful. And I do have shame, believe it or not. So we have x squared. That part remains the same. And then we have plus the square of 4x plus 7. So the binomial theorem goes like this. It tells us that we're going to square the first term. That gets us 16x squared. And then we're going to add the product of the two terms doubled. So 4x times 7 is 28x. And when we double that, we get 56x. And then we have the square of our very last term. So 7 to the second power is 49. And let me extend this. You didn't see anything. Now what we can do is we can combine some like terms that we have. Before we start taking the derivative, it's always in our best interest to simplify things as much as possible, to make things easier, to make things take less time, and to reduce the potential for error. You have a much lesser chance of making mistakes if you're working with a simpler thing, a simpler expression. So I'm going to combine these two together. X squared plus 16x squared gets us, you guessed it, 17x squared is our exciting conclusion. So that's all the simplifying we can do for now. Now let's just go ahead and take the derivative. We're going to take the derivative of L, the derivative of our length, with respect to our variable, with respect to x in this case. So it's always useful to take this and then make it into a 1/2 power. You can do that whenever you have a radical situation like this one. So let's just go ahead and do that. So I'm going to replace our radical with a 1/2 power. You know what? Actually, that may not be the best way to do it. So in general, whenever you're taking the expression, taking the derivative of an expression underneath a radical, the result, it's going to look like this. It's going to be u prime, where u is just everything that occurs on the inside, over 2 times square root of the function itself. So it's going to be, I mean, you can use if you want to verify this, you can just put all of this in parentheses. If you're more comfortable doing it this way, go right ahead. You could also do it like this, putting it to the 1/2 power, and then applying the power rule and the chain rule to get the derivative. But I just think it's a little faster to do things this way, a little faster, and it takes a bit less effort as well. So we're going to take the derivative of everything that occurs under the radical. So when we take the derivative of 17x squared, we get a 34x. When we take the derivative of 56x, we get 56. Put all of that over 2 times the square root of whatever was there from the beginning. 17x squared plus 56x plus 49. So this is our derivative. So remember that the process of optimization always depends on finding critical values. In this one, we may have just one. In other cases, we'll have more than one. And it's up to our own individual discretion to determine which one produces the result we're looking for. So let's go ahead, set this equal to 0, and then solve for x. So the really nice thing about this is that we can multiply both sides of our new equation by this entire nasty looking thing under the radical, this big scary looking thing. And we're left with just this. No more radicals to deal with, which is really nice. So now let's go ahead and solve for x, because we have x is just a single degree polynomial. That means we're only going to have one critical point. So let's go ahead and solve for x. So I'm going to subtract 56 on both sides, and then I'm going to divide both sides by 34. So we get negative 56 over 34. And if we wanted to simplify this, we could turn this into negative 28 over 17. Alrighty, right. So we already have our critical value. And by this point, we're pretty good at determining if this really does produce the result we're looking for. If it produces either the true maximum or the true minimum in a situation. If you want, you can verify it, but I'm just going to continue from here. We have our x. We need a y as well. We only have 1/2 of our solution. They're asking us for a point. We don't know the y coordinate, but that's pretty easy to find. Remember that we're trying to find a point on the line 4x plus 7. So to find the y coordinate, all we need to do is plug in x into this equation that we're given, and it will spit out a y value that will work for us. So we have y is equal to 4x plus 7. We're going to insert our x value. We're going to get 4 times negative 28 over 17. Plus 7. That's probably the biggest 7 I've ever made. move this. Whoa. Move this over here for now. Why did I make that 7 so huge? I don't know. Not sure. But we can go ahead and simplify this. So I want to have a common denominator of 17. 7 times 17 is going to be 70 plus 49. That gets us 119. So this is going to be negative 28 times 4, which is negative 112 over 17, plus 7, which is the same thing as 119 over 17. And as a result, we get 7 over 17. So that is our full solution. Our full solution is going to be this. It's going to be the point negative 28, 17, comma, 7, 17. And this is our solution. So if we look at the picture, it definitely makes sense that our x value would be negative and our y value would be positive. So this point right here, call it point P. This point produces the absolute least distance from this point to the origin.